Well, good morning, dear, and welcome back. So please join to the mask up campaign because the COVID situation is really bad at present, and we together can fight with this mask. So please wear mask whenever you go out. Okay. Nowadays, you need to wear double mask. Be safe. Now, welcome back. So we are continuing our discussion on uh, fuzzy logic with a special aim of how to develop a fuzzy inference system, right? And in my earlier class, we discussed that how a simple, with a simple example, we showed you that how fuzzy arithmetic operation can be done, how um, fuzzy function can be evaluated. Today, we will also discuss some uh, properties or feature of fuzzy membership function. And I must tell you that fuzzy logic is a huge area. Mathematics people are involved deeply here, so lots of, from their perspective, lot of theory and etc. has been developed over the years, and it has tremendous application in many fields, which we'll discuss in service sector, in engineering sector, in medical sector. So wherever you need to design an intelligent software or intelligent controller, fuzzy logic is always used. So naturally, the topic is huge, but we are trying to understand the core of it so that we can develop fuzzy um, inference or expert system so that we can use it for solving our uh, problems, right? And in doing so, whatever background we need to create, we are trying to create those background. So let us talk about a fuzzy membership function. This is an example of fuzzy membership function. As you can see, it's a continuous fuzzy membership function, and in fact, it is a trapezoidal membership function. Now it has some specification. You see, core. What is core? Core means, and you know, this is the X, that is the universe of discourse, and each element in the universe of discourse has some membership value, right? Determined by the fuzzy membership function. So what is a core in the membership function? Core is for those values of X such that the membership value of those X will be equal to 1. So anybody who is lying in between this, in this particular example, they are the core, right? So this is the core because all these um, elements has membership value equal to 1. So this is a core. Okay? Then support. Support literally meaning actually is support, as if it is supporting the fuzzy function, which is true. And for support are those X for which the membership value equal to 0. And boundary actually are those values of X which are lying in between the core and support. Support minus core is actually boundary. So for the elements lying in the boundary, their membership value will be between 0 and 1. Okay. Then also there is a concept called normal fuzzy set. You see, and subnormal fuzzy set. Look here. So this is a sorry. So here is a fuzzy set, triangular fuzzy membership function. Okay. So and see the membership value, the height of the membership function is actually 1. Membership value is 1. But what if the triangle size is like this, so that height is less than 1, that is say 0.6 or 0.7 here. So this is an example of subnormal fuzzy set. Subnormal fuzzy set. Okay. And this is an example of normal fuzzy set. Then what is a convex and non-convex fuzzy set? You see, this is an example convex fuzzy set. So this is universe of discourse X, okay, and this is the membership values, and this is the continuous function. Right? So it is a convex one because if you consider any 2 point on the universe of discourse, say A and say this is B, I'm considering another point B, okay. B, and in between say there is a point C, okay. Now to be qualified to be called as a convex fuzzy set, the membership value, what is the membership value? Say this is a membership value, right? A, okay. And what is the membership value of C? Incidentally, this is 1 here. And what is the membership value? Say fuzzy A, B. So if always, if C is lying between A and B, right? C is lying between A and B. We have considered 2 points A and B, and C is a point in between. And then if always the membership value of A, if it is always less than membership value of C, then this is called convex fuzzy set. Okay, convex fuzzy set. Whereas, you see, this is an example of non-convex fuzzy set. Say this is my 2 triangular membership function, inverse of discourse. So any 2 point, if I take A and say this is my B, and in between point is C. So here what is happening? Here the membership value of A is actually less than, I can just say so that vividly you can see, okay, A is actually greater than membership value of C. So although C is bigger than A on the inverse of discourse, okay, it should have been the case, then I could say that this is a convex fuzzy set. But here, you see, although C greater than A, the membership value of A is greater than membership value of C. So this is an example of non-convex fuzzy set. Okay. So this is my non-convex fuzzy set, and you can easily imagine that this set may be formed by union of this set 1 and set 2. Okay. So if I make the union, that means if this is my set, okay, so union of, so the triangular membership function, you know, this is always a convex fuzzy set because whatever 2 points you can consider, okay, and if the point is in the middle, and its membership value will be always greater than A. Okay, so this is an example of convex membership function, a convex fuzzy set. Sorry. Now you see union of, so this is one convex fuzzy set, this is another convex fuzzy set. Okay, but when I make them union, then I got a non-convex fuzzy set. However, if I take the intersection between 2 sets, which is this area, will be always giving a convex fuzzy set. So this is an observation which will be useful, maybe useful for many applications. So you understand, right, that union of 2 convex fuzzy set need not be always a convex fuzzy set. In fact, it will be non-convex fuzzy set in many cases. And intersection will always be convex fuzzy set. Intersection of 2 convex fuzzy set will generate always a convex fuzzy set. Then there is a concept called alpha cut. Very simple concept but very useful concept. It is used in defuzzification. Okay, and as we will discuss in greater detail that when we will design fuzzy inference system. say you will be having crisp input and you need to have crisp output in between fuzzy box. So what is happening there? Through fuzzy membership function, we will fuzzify the input variables. Then we will write down the rules. Okay, and when the rules will fire, you will get inferences or the output. That will be also in the fuzzified form. But that is not of use. I need to have a concrete output because my inputs are concrete. Okay, so we need to have defuzzification technique, and there are so many methods for defuzzification technique, which we'll discuss. So alpha cut is one defuzzification technique, and what it is very simple. You see, alpha cut, say uh, between 0 and 1 is a member. Say I have a continuous. Say I have a trapezoidal continuous fuzzy membership function. Okay, and whose elements in the universe of discourse, whose membership value lies between 0 and 1. Okay, so now suppose I am making alpha cut at say 0.6. That means I just draw one line at 0.6 membership value, and then I just intersect, I cut the uh, fuzzy membership function. Then the elements, whoever are here, their membership value be always actually greater than or equal to alpha, right? You see, greater than or equal to, for this, it is exactly alpha. For this, membership value is greater than alpha. This, greater than alpha. For this, greater than alpha. You understand, right? So, this is called alpha cut. So, again, if I just make another alpha cut, say alpha equal to 0.7, so then these are my crisp values whose membership value will be either greater than or equal to. Is it clear, right? So this is concept of alpha cut. Okay. Now this is used for defuzzification. Okay. Say I will just make a in mathematical form. You see, A alpha means alpha cut on fuzzy set A is a crisp set X such that this is a symbol of such that the membership value for all these X on the fuzzy set must be greater than or equal to alpha. Okay. Okay. So you see, greater than or equal to alpha. So here I can take an example. Say I have a discrete fuzzy set, not continuous like this. I have some, say within the universe of discourse, x1, x2, x3, x4. These are the four elements we have taken in the universe of discourse, and all of them is attached with membership value. X1 has a membership value of 0.9, X2 has a membership value of 0.6, X3 has a membership value of 0.5. Okay, so if I pictorially you can draw, okay, this is a this is a discrete fuzzy set. You can just draw. This is universe of discourse, or this is okay. So say X1 has 0.9, so this is 1, 0.9, 0.8, 0.7, 0. So say x1, 0.9, okay. So this one, x2, 0.6, 0.6. Say somewhere here, x2, 0.6, x3, 0.5. So the pictorial representation will be something like this, 0.5. Okay, you understand, like that. Okay, 0.3, So this is my pictorial representation of this fuzzy set. Now I am making an alpha cut, alpha equal to 0.6. So as per the definition, greater than or equal to alpha, all the elements, you see, so what are the elements will belong to this set, this set, whose alpha values will be greater than or equal to 0.6. X2 will be there, yes, because it is having 0.6. X9 will be there, yes, because its membership value is greater than 0.6. This will be there, no, because it is having less membership value. This will also be not there. Okay. So there is also a concept called strong alpha cut. Okay, when only the equal value is also taken care of. So alpha cut for alpha equal to 0.6 will be strong alpha cut will be giving you x1, that is one set value. Okay, because this is equals to 1. So equals to, if we just ignore equals to, it is greater than, right? So greater than equal to will give you this. If I just take strong alpha cut, that is greater than, then only one set will be there, because only this membership value is greater than this one. Okay, this one will disappear. Okay, because its membership value is equal to this one with the alpha cut. Okay, so this is very simple concept of alpha cut, which is giving you what you are getting, x1, s2, depending on what alpha cut you are doing. So if you are doing alpha cut 0.5, so 1 to x1, x2, x3, 3 elements will be there. Okay, is it clear? And if it is strong alpha cut, 2 elements will be there. Okay, because this will be disappearing, as I told you. So this is an example that alpha cut at 0.2 will be 0.2, 0.2, right? So this will disappear, this will be there, this will be there, this will be there. So like that. Okay, so you can generate by making alpha cut. You can generate by making different alpha cut. You can generate the set, grid set. Okay, so these are my grid set. These are my elements, right? So this is alpha cut. So this concept is useful sometimes. Now let us discuss something about different kinds of membership functions, which is the kernel of fuzzy inference system. There are a number of commonly used membership function. You can also design your own membership function. How? Say you have data, and if you try to make a regression analysis or do any statistical analysis to see what is the trend of the data, and those train in the form of a function can be useful for your particular problem as membership function. But otherwise, these are the standard membership function, fuzzy membership function, which are very, very useful, and they will solve your problem in most of the cases. So one is called triangular membership function. So this is a continuous triangular membership function. This is universal discourse. I have shown on a one figure many membership functions, so don't be confused. Okay, so say this is my point alpha, this is alpha point, this is the maximum height, point beta, and this is another point the triangle is making with the support is gamma. So alpha, beta, gamma. There are 3 points on the support. Okay. So I am defining. So this is being defined 0. This will be 0 if x is less than alpha, isn't it? For any value here, up to this actually, it is membership value is 0. will be equals to x minus alpha divided by beta minus alpha when your all the x values lies um, between alpha and beta, that is between this and this, and it will be gamma minus x divided by gamma minus beta when for this zone. Okay, so this is the triangular membership function, and again it will be 0 if x greater than gamma, isn't it? So anything here is very simple. Try to understand. So anything here, membership value 0. Anything beyond here, membership value 0. Okay. Now, so these are the two things are telling. So this parameterized by triangular membership function. X is the element in the universe of discourse. Okay, that is a variable, and parameters by alpha, beta, and gamma. Okay, so how this you are getting x minus alpha divided by beta? Oh, it's just very simple. This similar triangle. Okay, so this one and this one. What is this one? This one is 1. Membership value is 1. Okay, and I need to figure out what is this membership value. Say this membership value is unknown, right? I am trying to finding it out. So what is the nomenclature I will give? Say Z, unknown. So this is triangle A, B, C. You consider this triangle A, B, C, D. Okay. So in this triangle A, B, C. Okay. D is a point here. This is parallel to the height. So what will be this value? Z divided by BC equals to AD divided by AC. Clear? And this is equals to 1. So Z equals to AD divided by AC. So this is what we have written. What is AD? AD is nothing but x. D is any point which is representing x. So x minus alpha, that is AD. Okay, divided by AC. AC. Okay, what is AC? Um, AC is actually from here to here, beta minus alpha, beta minus alpha. As simple as this. Just draw this similar triangle, class 12, geometry. This divided by this equals to this divided by this. Okay, and similar is the case. Okay, so you need to figure out for any say Z value here. Again, similar triangle C, B, say here C, B, E, F, G. So this is a triangle. Now this is also a triangle. We will use it very frequently. Okay, so you need to figure out FG. So same. Do I need to do it again, or you can do it now? Okay, you can do it. So GF divided by 1, because this is 1, equals to FE divided by CE, and then this is equal to FE equals to gamma minus x. X is any point here. Okay, and divided by gamma minus beta is this one. Okay, see, so as simple as this. So that's how we have defined a triangular membership function. Great. Now here we will see any question. If you have any question, you can come to the discussion forum or comment box. It's very simple. We have defined triangular. Now trapezoidal membership function. Here is a continuous trapezoidal membership function. Say we have, okay, which is parameters by A, B, C, D. Okay, so the value will be 0. Value will be 0 if x less than A. So this is A, This is B, C, D. Okay, isn't it? If x is anywhere here, the value is 0. Function membership value is 0. And then if x is lying between A and B, any value A and B, so this is a say. So this is your A, okay. So this is a triangle, and this is parallel to the height. Okay, so this is height is 1. So this say z divided by 1 is equals to this divided by this one. Okay, so x minus a divided by x minus b as earlier. Right? It's a similar triangle. So this, okay, this you are getting equals to 1 when obviously anything lying between this and this, everybody's membership value is equals to 1. And when x lies between C and D, as I have deduced using similar triangle, you can deduce exactly that this is the definition. Okay? And of course, beyond there, this is 0. Then also there is a membership function called Gaussian membership function, which we have shown here. Parameters by center and width sigma, okay, and center. Okay. So these are the two parameters. Playing around with this, actually, this you can playing around with this width. You can make it like this. So width is smaller, okay. So you can make it more flat. That is, width can become width bigger. It's all kind of things. So these are the controlling parameter. Okay, center means where the it will lie. But remember, this is not Gauss function as you have seen in statistics, right? So similar function, same formula, but these are not statistical parameters. So these are my parameter here, which analogous to statistical parameter, but they are signifying width and center of this curve. So if I see some of my membership function train, some of my membership function, that is Gaussian membership function, can meaningfully fuzzify my input, then I can use Gaussian also. Formula is same, e to the power minus x minus m squared divided by sigma squared. Then there is a Bell-Shaped membership function. Okay, so you see they're defined by 1 plus x minus c by a to the power mod of this to the power 2b. Okay, so here this is 2a. Okay. This is a crossover point, 0.5. 0.5 is half of the membership value. It's called crossover point. So this is a Bell. It's just like Bell. Okay, and gradient of this Bell-Shaped function is, you can see, this angle is minus b by 2a. Okay, can be, you can just deduce. B controls the slope at the crossover point, right? So it will be like this. It will be how means will it be like this? Okay, this is also Bell's effect. So this is a crossover point. So B controls that, okay? And the formula is given by this. Okay, this is Bell's effect. Sometimes it is used Bell's effect function, and then sigmoid function also as a membership function used. There are many more actually. So these are very commonly used, and as you know, that sigmoid function is parameterized by a and b. You see, this is my sigmoid is an asymptote at a and b, and m is actually midpoint a plus b by 2. So if this is a, this is b. So in the midpoint, that is crossover point, you know, this is, you know, if you do not know, you know, this is my sigmoid function, and crossover point at 0.5 where it actually changes its gradient. Okay. So, and the different definition of the function is like this, that if x less than a, means somewhere here x value, membership value 0, and then if between a and a, that is anything between this and this. Okay, so the value is 2 x minus a divided by x minus b minus a squared. Okay, so this is directly coming from the definition of sigmoid function. Okay, so perhaps you know. This is a sigmoid function, and then membership value 1 minus 2. So please deduce, check it. If something beyond this, the membership value will be actually given by this, and membership value equal to 1 for anything beyond this. Okay. Well, so these are some of the very commonly used fuzzy membership function which we have introduced, and we will be using them in future, and we'll discuss now using this membership function how I can capture knowledge from the expert, because in fuzzy logic we are all trying to do that, and especially in artificial intelligence domain we are trying to design a fuzzy expert system. And in designing that expert system, I need expert's knowledge. Okay, an expert will talk in a very ambiguous way, and fuzzy logic together with fuzzy membership function, fuzzy set, fuzzy arithmetic, they are all helping me to capture the knowledge and manipulate the knowledge. So we'll continue our discussion on how to capture knowledge from an expert using fuzzy membership function and using logic, if and then logic, if and then. Okay, so in the next class. Till then, stay tuned, please. And don't forget to wear mask. Have a nice day. Bye bye.